All right. Well, I hope everybody's doing well. Just a reminder about the schedule that's posted on Blackboard, you know, the course schedule. It has laid out for the whole semester, day by day, what's the topic of the class meeting, when is the due date of each assignment, and you just turned in homework 2 today, right? Like 5 minutes ago, maybe?
I actually turned it in last night.
All right. So the homework 3, you got a little bit of a quicker turnaround. You know, sometimes it's a 1-week gap between assignments. This one is due on Wednesday. You know, can you believe it? I've had some students say that there's too much work in this class. But actually, after my own sons have taken some Marshall classes online over the summer, you know, they took psychology and a history class. I couldn't believe how little they actually had to do. And I'm starting to realize is there are some other classes that are easier than engineering classes. You know, engineering classes are maybe a little bit more work than some of the other disciplines on this campus. So in any case, I'm going to work you to the bone in this class, but at the end of the semester, you're going to know a lot, and you're going to have some skills that will be really useful. So hopefully you don't resent the fact that it's just going to be coming at you from every direction, and the manifestation of that that's most immediately on your radar is homework 3 due on Wednesday. All right.
I've actually took a peek at homework 3, and I noticed that it actually has a lot less questions than this week's homework.
Okay.
There's like 4 on here.
Yeah. Yeah, sometimes there are more short questions. Other times there's a fewer number, but the questions will each take a little more time. I mean, in general, I hope that they'll take about the same amount of time from assignment to assignment, but, you know, sometimes there will be quick ones and other times there'll be long ones. But the one thing that will remain constant is I'm always really eager to help you. So you can stop by my office hours, give me a call on Teams, send me an email. I love questions. I hope you can tell that I really find this stuff interesting. And what I like even more than the material is helping other people to understand it. So, you know, I'm here for you 100%. I'm all in on this class. So today we're going to talk about gradients, which is maybe the more complicated unknown that we haven't addressed yet. So let's just review what we have seen so far in terms of P, F, and A. All right? So an annual series, remember, should be an unbroken, constant amount with no gaps that's repeating, period by period. And so this representation, the cash flow diagram you see on the left, would be find P given A. And then using the standard notation where we can look up factors or calculate factors with the equations, then we would multiply the amount of A, meaning, you know, the amount that 1 year of those payments would be. You'd multiply it by the result of the factor. What's inside the brackets is going to be some factor you can calculate or look up, and then that would allow you to calculate P. And in this case, it's essentially asking how much do you need to deposit now to be able to take 5 equal annual withdrawals, and then it's implied that at the end of the 5th year, there would be no more money left in the account. That these 5 equal withdrawals would be in balance with the initial deposit that had been made at year 0. So all that's implied by this picture. The other way around is sometimes the annual series will be the unknown, and P is the given amount. And so the way that we would interpret this is how much could you withdraw each year for 5 years from an account when you make a certain deposit at time 0, and then at the end of the 5th year, you would have withdrawn the last penny from the account. So it would be in balance, economic equivalence between the inflows and the outflows, economic equivalence between what's at the present and those amounts in the future. So we would calculate the magnitude of these arrows by multiplying P, the known present value, by the quantity inside of the factor. All right, and we can look those factors up from tables, and also there's the equations that are in today's in-class exercise paper, we're going to do it both ways, just to reinforce. Now, what's a little bit more, I don't know, it's kind of strange in a way, is if the future value is desired. So what's kind of summarized or implied by this image is, let's say that a year from now, you get a certain amount of money. And then every year for 5 years, you get that same amount. How much would you have to pay back as a lump sum 5 years from today to bring equilibrium between inflows and outflows? In other words, I don't know why this would happen, but you get your 5th payment at the same time that you're repaying the loan. That's one of the things that's a little bit strange about future values with an annual series, is that the future value is in the same year as the last of the annual amounts. So when you find F given A, it's in the same year. It's not like a year later. That's just the way it is. So again, we could multiply that by the factor that we look up or calculate. Other times, the annual amount is the unknown, and we know a lump sum future value. So that might be the situation where you know in 5 years you're going to have to make a lump sum deposit to somebody. So that could be like a bank, or there are companies, insurance companies, that sell annuities where you're receiving constant income every year or every month. And usually you would give a lump sum to them up front at the beginning of the period. But let's just say hypothetically that instead you've negotiated a contract where you get regular income, and then at the end of this time period you have to make a lump sum deposit. So with this scenario, you would be knowing the amount that you're going to have as the lump sum, and you could calculate the economically equivalent annual withdrawal amounts that would bring balance between the inflows and the outflows. So this is F and A, future values and annual amounts. So just as a quick illustration example of that, let's say that an engineer has changed a production process and is now saving the company $10,000 a year. Now, this word save, you got to be cautious about the word save, because if you are putting money in the bank, if you're saving money, that means you're taking money from your pocket and you're giving it to the bank. And so that is an outflow when you save money, like invest or deposit. Those are the synonyms that I mean by that kind of save. But there's another kind of save. This isn't talking about making deposits to a bank. What is this use of the word save talking about instead?
Money that they would have spent that they won't.
Money that they would have spent that they won't. So that is the same as revenue. From an accounting perspective, if you used to have some expense and then you make a change and your expense is lower than it used to be, that's kind of like now you're getting paid that amount. So that change is effectively an inflow. So what this statement is saying is, this engineer figured out something that's going to save the company from an expense they used to get. So effectively, the company gets $10,000 a year because of that change. And so this question is saying, at 8% a year, what's the lump sum single value future amount that's equivalent to receiving 7 years of $10,000 inflows? So when I do a cash flow diagram, these arrows are up. They're not down. The company isn't depositing money into an account. They're receiving a reduction in their expenses, which is the same as an inflow. So that's why the arrows are up. But just to visualize here, every year for 7 years, the company gets $10,000. And we want to know what would be the future equivalent of that. So is it 10,000 times 7?
No, because the interest like stacks.
Because there's interest, right. Remember, money now is more valuable than money in the future. And the reason why money now is more valuable is because things in the future are going to cost more money than they cost now. So $1 today can buy more stuff than $1 in 7 years. In 7 years, you're not going to be able to buy as much stuff because prices will be higher. So it's not just as simple as multiplying 10,000 by 7, because that approach would ignore the time value of money. This table accounts for the time value of money. And the 7% interest, the 8% interest rate tells us how much the money is compounding or discounting, depending on whether we're moving it forward in time or backwards in time. All right. So we would go to the table. For 7 years, the factor is 8.9228. And so the value of the future amount, 89,228, is how much you would have to get as a lump sum in year 7. So if they're going to delay paying you, you want more than just the same number of dollars, because it's more valuable to get the money as early as possible. So it makes sense to me that it would need to be more than 70,000 in year 7, because in year 7 the prices are going to be high. So you want more than just 70,000. You want 89,228 for it to be economically equivalent. Okay? So that's how we would find F given A. All right, now gradients. This is where the rubber really meets the road. Gradients are a bit strange, but they do occur when an expense is increasing over time. And plenty of things get more expensive. Think about the maintenance on your car. It might be conceivable that this year you're going to have to spend $100 maintaining your car. And then next year you're going to have to spend $200 and $300 the year after that, because it keeps getting less reliable and it's breaking down more. And maybe it wouldn't be exactly $100 amounts, but sometimes just for planning purposes, we could model it as an increase that is progressing along a linear path. And so that's what the gradient idea is that with each year there's a change, and the magnitude of the change is the same amount for each period. So you can see here, just as an illustration of a find P with a given gradient, that the form that we've decided on, the standard notation or the convention for figuring these out, is that the present is times 0. And 1 year from the present, there is 0g, meaning that there's no amount associated with the exchange. But then in year 2 is g, and g could be $100, it could be $1,000. It's just some certain amount, whereby in the year after that, it's double the amount, the following year is triple, and so on and so forth in as many periods as there are in the series. So this would be what it looks like when you are finding P given G. And the key things to remember, like the greatest hits of mistakes that people make on homework and exams, is forgetting that delay year. That the gradient, you actually see the effect of the gradient at the end of year 2. So here's year 1. Year 1 is from time 0 to the end of the first year. So this is year 1. Here is year 2, and at the end of year 2 is where you first would see the effect of the gradient. So just another way of saying that is that when you find the present value of the gradient, it's 2 periods earlier than the first time you saw the gradient amount. So there's a gap there. Yeah.
So is that because like you're measuring like the difference and not like the actual worth of like what you're paying? So it's like year 1 you're paying like a base amount, and then like the G after that is like the difference between like how it's increasing?
That's one way to think about it, yeah. I think that, it's sometimes hard to know exactly why these conventions ended up the way that they did. I think it's possibly just because when you combine a gradient with an annual series, which you'll have one of those illustrations in today's in-class exercise, that sometimes you can have a gradient on top of other things. that you'd want in the year one to be able to see just the effect of the annual series itself without the gradient contributing. So that may also be another part of it, is when gradients get combined with other payments. Okay, so let's pull open the in-class exercise for today and look at what we are going to be working on. I'm almost a little reluctant to ask if there's anybody who hasn't printed them yet. I don't want to head into the weekend with that heaviness in my heart if there's somebody who still hasn't printed them yet. All right, so we've got the equations. We've got the factor table. The first problem isn't a gradient problem. The first problem is just, it's P and A in the first problem. But the second one is a gradient problem. And what I have done here is I haven't even put the years in the cash flow diagram. I've just got the tick marks. And so you can see that on part A of that question, I ask you to write the years on the cash flow diagram so that you can start to get in the habit of noticing the gap between when a gradient begins and time zero. Okay, so just a little bit of a preview on that second problem, and then on the third problem, we have a gradient and an annual series. And so this one's a little bit trickier. What I suggest you do is solve, let's focus on problems 1 and 2 for now, and then after we've had some time to work on it, and it seems like most people are there, I'll pull the solution up, we'll go through it together, and then I'll give you some additional hints on how to begin problem 3. You're welcome to get an early start on problem 3, but because it's a little more tricky, some people may benefit from the hints I give you before getting started. All right, so the time is yours to be working on problems 1 and 2, and of course, it does not need to be quiet in here when we're working on these in-class exercises. I love it if you scoot next to a classmate, collaborate, discuss, explain, all that good stuff.
The interest, okay.
At 8% interest, this is per period, annually? That's always the assumption in this class?
Unless it says the period is something other than years. 8% means per year, 8% per year, or per period, yeah. And it says here annual. All right, let's take a moment to make sure that we're all on the same page with what the answer should be for problem 1 and problem 2. So let me pull up the solution for that. Okay, problem 1. Like I've said before, sometimes just interpreting the problem statement is the trickiest part. Translating the words into a cash flow diagram. So, all right, it says, if you give a $7,500 loan at 8% interest and the loan should be repaid in equal amounts over 8 years, how much should each annual repayment be? All right, so a loan begins with a transaction at time 0. So this $7,500, although it doesn't say you give someone $7,500 at time 0, just the default built-in assumption here, unless it says otherwise, is that the loan transaction between parties is at time 0. So this is a present value. Now the 8% interest, that is the interest rate per year. That's the other kind of default, unless something else is specified in terms of monthly compounding or simple interest is so rare that it would have to be explicitly stated in the problem statement if this was a simple interest type problem, but it's not. This is a compounding interest problem. So P is 7,500, I is 8%, and N is 8 years. All right, so then I did this one, since I had the 8% table right there above it, I used the table lookup method. It's okay if you preferred to use the equation method, but the factor that I looked up off of the table, 0.17401, Multiply that by 7,500, and so it tells you that each one of the repayment amounts should be $13.05 and 8 cents. Now remember, though, that we have to round off to as many digits as there is in the factor. So if you did the equation method, you could solve this to the nearest penny. If you do the factor method, you can only solve it to the nearest 1, 2, 3, 4, 5, to the nearest 10 cents. And so the answer, $13.05 and 10 cents. I think the people who did it according to the equation method got $13.05 and 11 cents, right? Okay. So any questions about this first problem? Even though it didn't say you had to, it's not a bad idea to sketch a cash flow diagram. I mean, you're never wasting your time if you make a cash flow diagram. It can help you to visualize really what's happening. Okay, so problem 2 presents this, where the first tick mark is times 0. 1, 2, 3, 4, 5, 6. Now that doesn't mean that n equals 6 just because there's 6 tick marks on the line. N is going to be 4 because that's the last year that something happens in this gradient. So from the perspective of like where's the gradient at, n equals 4. So the first part of this is going to be to write the years on the cash flow diagram, and you can see how I've done that. 0, 1, 2, 3, 4, 5, 6. N equals 4 and G is 200. G just means what's the amount that it's increasing by with each passing year. And so it was 200, then 400, then 600. So you can see that the incremental amount is 200. So that's what makes G 200. It's the value of that increment. Find the present value. That is to say the amount in year 0. So I'm just saying by present value, I don't mean take it to year 1. I'm reinforcing the notion that when you're finding a lump sum present equivalent, it's 2 years before the first G that you actually saw. So we saw the effect of the gradient in year 2, and so we go 1, 2 years back in time to times 0 in order to find our lump sum present value of that. So that's what I mean. That's why I said in year 1. And so the hint that I give you here is use the P to G column in the 8% table. So this is find P given G. So if we go to the table, find P given G for n equals 4, 4.6501. And what we do is multiply 4.6501 by G. So this first term inside the parentheses, P divided by G, that's just a reminder that, you know, this is a ratio. This 4.6501 is a ratio of the present value to the gradient amount. So if you want to find the present value, you multiply the gradient amount by this numerical factor. And so that's what we did, multiplying it by 200 to get $930.02. All right, and so how am I doing on round off here? I've got 1, 2, 3, 4, 5 significant figures, and there's 1, 2, 3, 4, 5 significant figures in my answer. So I can be accurate to the nearest penny in this problem, even though I use table lookup, because there's as many digits in my factor as there are in the final answer. All right, find the future value, meaning the amount in year 4. Use the the F to G equation. And it's a pretty complicated equation. Here is the F to G equation. There it is. Okay, so it's got a couple of terms. There's a lot going on here. I took my time with that substitution. I wasn't rushing it. First writing the formula, then substitute in I and N. And you can see here with these brackets, I'm trying to kind of group together terms. And in the end, the factor, the ratio of F to G is 6.3264. So if you multiply that by 200, then you'll get the future value should be $12.65 and 28 cents. All right, now, this one. we have both an annual series and a gradient. They're both happening at the same time. So you could look at this cash flow diagram as there is 400, 400, 400, 400. And how many does it go? 5. So here's 1, 2, 3, 4, 5. A equals 400. And also, in addition to that, then there's a gradient thing happening where there's nothing at year 1, 2, 3, 4, 5. So then the gradient kicks in year 2, and it's 30, 60, 90, 120. 30, 60, 90, 120. And so in that case, G is 30. So what I'm saying in this problem 3 is find out what is P for the annual series, and then what is P for the gradient series. And then you combine them together, and that's the sum of the present value, the total present value for this entire cash flow diagram. So we're breaking up into its constituent pieces. So let me pause for a second. Maybe you're already well underway, but this is a problem where we're using the same approach as before. You're going to have to, for the 12%, you can't do the table lookup. You'll have to use the equations for 12%. Find P given A, and find P given G, where A is 400, G is 30.
I'm not really sure what this means. Like, I got this, but I'm not really sure what that represents.
Okay, we're running out of time, so let's look at the solution to the third problem. We've got an annual series where A is 400, and there's also a gradient on top of the annual series where G is 30. Okay, so the two things we're going to do is find P given A, and then we're going to find P given G. So here you can see I've got the two component series together. All right, so the present worth of A, if we use the equation method, the factor should be 3.60477. And what do these little dots afterwards mean? When I have the dot, dot, dot? It means I didn't round off in my calculator. There's more precision there. I'm not going to bother writing it all on the paper, but I didn't round off yet. And that's what allows me to report my final answer to the nearest penny, is that I didn't round off until the very end here. So 1441 and 91 cents is the present value of the annual series. Did anybody else get that same value? Yes. All right. Now the gradient, remember, it first shows up in year 2, and so it's G, 2G, 3G, 4G. So here's the formula for finding the ratio of P to G. Okay, so you can see we've substituted 12% for I, n equals 5. And so the ratio of P to G, 6.3970. And I assume that maybe that continues onward, but I just didn't round off yet. So $191.91. And so the overall present value is the combined annual series and the gradient moved to the present. So $16.33 and 82 cents. All right, that's all I've got for you today. Hope you have a great weekend. And if you've got any questions on this new homework assignment, let me know. I'm here to help.
What's your name? Clay.
final.